So we looked at an example of how to graph a rational function where the degree of the numerator and denominator is the same. Now we're going to look at some properties of rational functions. So one of the properties looks at slope. Sometimes the question might ask you whether the slope is positive or negative and whether it's increasing or decreasing. And so there's a couple of different ways you can do this. First of all, you can compare the slopes of secant lines in each interval. So you can look at the segment of the function to the left of the vertical asymptote and then the segment of the function to the right of the vertical asymptote, and look at a couple of secant lines and compare whether the secant line has a positive or negative slope and whether the slope is more positive or less positive or more negative and then less negative. So you're just comparing to see what's happening with the slope. Or your other option is to choose 2 points in each interval and then compare the y values going from left to right. So there's a couple of different ways that you can look at slope. Okay. And then there are positive and negative intervals. And then in this case, all you're really doing is looking at the sign of the function. So you start by choosing a test value in each interval, and then you determine whether the function is positive or negative in that interval. So we'll take a look at both of them. So starting with slope. So here you can sort of see the rational function that I had drawn before. It's in pencil. And so what I did is I drew 2 secant lines in each of the segments. So if you actually look at this function, you'll notice that the secant line for both segments is actually negative. Okay, so that means the slope of those lines are all negative. Now what you have to try to recognize is whether it's a slope that's increasing or if it's decreasing. So the way I used to look at it, it's easy when it's both positive slopes, but when their slopes are negative, it's a little bit more challenging. So this is how you may want to think about it. So if I follow this pencil along the first line or along the first secant line that I drawn, I'm going from a less negative secant line to a more negative secant line, which means I'm actually decreasing in terms of the slope. Okay, so because we're going from less negative to more negative, the slope is actually decreasing. Okay, so it's negative, but it's also decreasing. If I look at the second segment and I look at the first secant line that I had drawn, I'm going for from a more negative slope to a less negative slope. So if I'm going from more negative to less negative, that means that the slope is actually increasing in this segment. Okay, so think about whether your slope is going from more positive to less positive, or if it's going from more negative to less negative. So compare more or less what's happening with the slope, and that'll give you an idea of whether it's increasing or decreasing. Okay. In terms of positive and negative intervals, so what you want to look at is the sign of the function. So anywhere there's a significant change in the function, so wherever there's a vertical asymptote or wherever there's an x-intercept, those are the kinds of intervals you want to focus on to see whether the function has a positive interval or a negative interval. So here I've drawn a rational function, and I've broken it up into 3 intervals. The first interval goes from negative infinity till the first x-intercept, or the only x-intercept that I have. The second interval goes from the x-intercept to the vertical asymptote, and then the third interval goes from the vertical asymptote over to positive infinity. Okay, you'll notice that there's a significant change in the function along those 3 segments. So the first segment, if I look at it, or the first interval, if I look at it, the function is actually above the x-axis. So that means that this is where it's actually positive. In the second segment, between the x-intercept and the vertical asymptote, you'll notice that it's actually below the below the x-axis, so that means it's negative. And then in the third segment, from the vertical asymptote to positive infinity, the graph is actually above the x-axis, so it means it's positive. So one way to do it is to choose a test value in each of these intervals and see whether the function is positive or negative, and that'll tell you if it's above the x-axis or below the x-axis. The other way is to look at it graphically and then figure it out based on that. Okay, so those are a couple of the properties that we haven't looked at in a lot of detail yet, so we wanted to show you guys how you can recognize whether the slope is positive, negative, increasing, or decreasing, and whether you're looking at a positive or negative interval. Okay, so please don't confuse these two. Slope looks at something very different than the actual sign of the function. So we'll look at another example. And in this example, we're going to graph the following rational function. So again, you'll notice that we have a linear function over a linear function. But this time you should recognize that I can actually simplify the numerator a little bit more. Okay, so I'm actually going to simplify the numerator, and I'm going to factor it out to get 4x minus 2 over x minus 2. And what you'll notice in this case is that I do have a restriction such that x cannot equal to 2. So that's actually where my vertical asymptote would be. Except if you notice in the numerator and denominator, there's a factor that's common in the numerator and a factor that's common in the denominator that I can reduce. So what this leaves me with is h of x equal to 4. Okay, where x cannot equal 2. Now this is interesting. This is actually the equation of a horizontal line at y equal to 4. But now our vertical asymptote has now been reduced away and it's become a hole in the graph. Okay, so the restriction is still there, but this time when you're graphing a rational function, when you have a factor in the numerator and denominator that are reduced away, it ends up creating a hole in the graph. So I'll draw a line at y equal to 4, because that's where the actual line is. And then we'll recognize that there is a restriction on the function at x equal to 2, and that restriction will be modeled by a hole in the graph, okay, or a break in the graph. Okay, graphically we just show it as a hole. So there is a function h of x with a gap at x equal to 2, since there is a hole at that. There's a hole at x equal to 2. Okay, there's a restriction there. Okay, so just to summarize everything that we've looked at for a rational function, where the degree of the numerator and denominator are the same. First of all, the vertical asymptote is a value of x that will make the denominator equal to 0. The only time there is an exception is if the numerator has the same factor as the denominator, which will end up resulting in a hole in the graph, just like we saw in the last example. And then horizontal asymptote, because the degree of the numerator and denominator are the same, you can find the horizontal asymptote just by focusing on the leading coefficient in the numerator and the leading coefficient in the denominator. And so it's just a ratio of those two leading coefficients. In terms of x-intercepts, the way you would find an x-intercept is any value of x that will make the numerator of the function equal to 0 will result in the entire function being equal to 0, which is where your x-intercepts would be. So whatever the zeros of the numerator are, those are the value of x that will make the function equal to 0. Okay, and so that's where you can find your x-intercepts. In terms of your y-intercepts, if you plug in the x equal to 0 into the function, what you end up getting is these two terms disappear, and you end up having b over d, so your y-intercept ends up being b over d. Okay, so those are the only values that remain in the function, so that's how you would quickly find your y-intercept. Okay, and then what does the value of b and what does the value of d actually do to the function? So the value of b actually stretches the curve horizontally and vertically, so it sort of moves the curve slightly here. So it bends it further inwards or bends it further outwards. So that's really all it does. It doesn't affect the asymptotes or the domain or range. It just sort of changes the curvature in the graph. And then the d value actually shifts the vertical asymptote. Okay, so depending on what the value of d is, it shifts the vertical asymptote left or right. Okay, and the last little bit that talks about the properties of rational functions is that the two branches of the graph, so this branch here and the branch on the left here, are actually equidistant from the point of intersection of the vertical and horizontal asymptotes. So here I've drawn the vertical and horizontal asymptotes, and the points that you have on one end are an equal distance away from this point here where the x and y, the vertical and horizontal asymptotes intersect. Okay, and that's it.